So, welcome to lecture 4. And in this lecture, we are going to talk about some numerical examples on DC machine types and EMF equations. So, in the earlier lecture, we had listed out various types of DC machines and like separately excited DC machines, self excited DC machines, long shunt, short shunt, series, and all these kinds of DC machines. So, the different types of DC machines we had seen, and also we had seen the EMF equation. So let's just quickly refresh. So what is the EMF equation for the machine? So if you look at the machine, what comes to your mind? One is the poles. So the DC machine has the poles, and the more number of poles are there, the more flux will be there. So therefore, EMF generation will be more. So P is directly proportional. So I put P in the numerator. Similarly, N is the speed of the machine. Phi is the flux of the machine. So as I rotate the machine faster, the rate of change of flux linkages will be more and Eg will be more. Similarly, as each flux, so phi is here flux per pole and P is the number of poles. So P into phi is the total flux. So even that also will be more. And there is a 60 in the denominator, which is just converting the speed in revolutions per minute. By 60 you will get speed in revolutions per second. So that's the constant. And then another constant we had was Z by A. So EMF, so Z is the total number of conductors, but of course all the conductors are not connected in series. So therefore, the certain conductors are divided into parallel paths. So if there are 4 parallel paths, then all the conductors, like 400 conductors if they are there, 4 parallel paths. So each path will have only 100 conductors. So therefore, the voltage will be proportional to that actually. So therefore, that's why this will come. And this was the expression for EMF generated in the machine. And then different types of machines we had seen. So for example, shunt machine will look something like this. Uh, so of course, armature resistance will also be there. And then there is a load. So we have seen shunt, this is H. And then we had seen series. And then we have seen compound. And in compound, it will have both series and shunt windings. It will have long shunt and then short shunt. So let's continue. So now what we'll do is we'll solve a series of problems which combine these two concepts. So I might use both this uh, circuit and then the EMF equation and then try to solve some problems. So let's move forward. So here you can see an 8-pole DC shunt generator. So this is example number 7 and previous examples we solved in the previous lecture. So let's do that. So you can also try attempt your solution yourself and you can compare your solution with my solution. You can pause the video now and you can try it. And let me also solve this problem now. So example 7, an 8-pole DC shunt generator. So poles are 8 and then DC shunt generator 800 wave connected armature. So Z is 800 and since it is a wave connected, parallel paths are 2. Running at 600 RPM, so therefore speed is 600 RPM. Supplying load of 12 ohm resistance at 60 volt terminal voltage. So RL load resistance is 12 ohms and then the terminal voltage is 60 volts. I'm just writing down the data that is given. Armature resistance is 0.25 ohms, so 0.25, and the field resistance is 250 ohms. So I'll define it as RSH 250 ohms. Find the armature current induced, comma, induced EMF and flux per pole. So let's see. So it's a DC shunt generator, so it helps in drawing the diagram. So this is a circuit diagram. So this is a DC shunt generator. Load resistance is 12 ohms and the load voltage is 60 volts. So therefore the load current will be nothing but division of these two. So 60 divided by 12, so that will be 5 amperes. So here I'm sure I'll be getting 5 amperes. 12 into 5 is 60. What about the field current? So this is 250 ohms. So the field current maybe I can calculate. So the voltage is 60 volts. So ISH shunt current or IF will be voltage 60 divided by 250. So let's calculate what it is. So 60 divided by 250. So 0.24 amperes. So here I'm getting 0.24 amperes of current. So simple Kirchhoff's current law at this point will give you what is IA. So armature current is nothing but 5 plus 0.24. So I'll get 5.24 amperes. This in turn will give me the drop in the armature resistance. So this is 0.25 given in the question. So therefore IARA will be the drop. So let's calculate that. So 5.24 multiplied by 0.25. So let's see how much we get it. So multiplied by, I'm sorry. So 5.24 multiplied by 0.25. So I'm getting 1.31 volts. So this much voltage is dropped here. So therefore the total voltage is 60, the voltage drop is this. So now I can find what is the EMF induced in the machine. So that is EG is nothing but 1.31 plus V. So 61.31 volts, which is nothing but V plus IARA. Now EG also I can know from a different formula, because in the question flux per pole is also asked. So EG is nothing but phi Z N P by A into 60. So I keep changing the order, but don't worry about that. So from this I can find the flux. So what is flux per pole? So that is nothing but EG into 60 into parallel paths divided by N into Z into P. So I have all these values. So EG I just calculated 61.31 multiplied by 60 multiplied by A. So what is A? So here I had written A is 2 and N is 600. Just remember these values, 808. So two parallel paths, speed was 600, conductors were 800 and the poles were 8 poles. Yeah. So therefore now I can find what is the flux. So let me again use the calculator. So I have 61.31 multiplied by 60 multiplied by 2, then divided by, I open the brackets, so 600 into 800 into 8. So I'm getting 0.0019. So this is in Weber, so I'll round it off to 2 milliwebers. So this is the answer. So I hope you learned something from this problem. That is, we had to find induced EMF, we had to find the armature current, we had to find the flux per pole. All these things we had found. So that is the solution for this problem. So let's move forward and let's do one more question. This is example 8. So in which a separately excited generator is given. So again, it helps to draw the diagram. So I draw the separately excited generator. So there is a voltage and sometimes there is a variable resistance. So by, just close this other one. So by changing this resistance, which is connected in series, I can control the current in the field. So that is the idea. A separately excited generator when running at 900 RPM. So let me also So this is RA and this is the EMF generated, EG. So this is plus minus. A separately excited generator when running at 900 RPM supplies 180 amperes at 120 volts. So this is 120 volts and it is supplying 180 amperes to a load. What will be the load current when the speed of the prime mover drops to 760 RPM? Okay, so here N1 is 900 RPM, N2 is 760 RPM. When the field current is unchanged, so field current is not being changed, so therefore flux is constant, flux is unchanged. Take the armature resistance, so RA is 0.04 and total brush drop 2 volts. So let's first calculate the drop here. So what is the IARA? So in the previous case 180 amperes multiplied by 0.04, so that will be 180 multiplied by 0.04, 7.2 volts, and here this is 120, so therefore EG will be 127.2 volts. Now we know that, so this is EG1, let me denote it as. So EMF generated EG is proportional to flux and speed. So we had earlier seen that. So if I just go up quickly. So in this formula, so if you see, Ka multiplied by flux into speed. So the poles are constant. You cannot change the poles of the machine suddenly. Number of conductors you cannot change. Parallel paths you cannot change. 60 is also a constant. So if I take this entire term and denote it as Ka, then Ka into phi A, you will get it. So this is a one more thing that we get from it. So therefore, I can write here Eg1 is equal to phi 1 N1 by Eg2 equal to phi 2 N2. But then here the field current is constant, therefore flux is constant. I can just consider these two are equal. So therefore this is the relation I am getting. So therefore what is Eg2? Eg2 is nothing but Eg1 multiplied by N2 by N1. So therefore 127.2, and now the current speed is 760 RPM. So here you see speed is reduced to 760. So as speed is reduced, even the EMF also will be reduced. So what is that? So let's calculate this. 127.2 multiplied by 760 and divided by 900. So this is 107.41. So now Eg2 is less. Now with this Eg2, what will be the load current when the speed? So for that, first I find the load resistance. So what is the load resistance? Load resistance is nothing but voltage of the load by current of the load. So voltage of the load was given to be 120. So 120 volts by current is 180 amperes. This is before the case. So that is 120 divided by 180. So I get 0.67 ohms. Therefore, total resistance, now if I look at the circuit, so I have Eg2 is equal to IL into RA plus RL. So therefore, I'll find IL something like 107.4 divided by 0. What is the RA? 04. 04 plus load resistance is 0.67. So this will give me the new load current. So 107.4 divided by 0.04 plus 0.67. 151.26 amperes. So the current also has reduced. So I think now let's continue with example 9. So here is example 9 on your screen. So you can try it yourself and you can also check your answer with my answer. So let me start answering this question. So what do I have? A 4-pole lap wound DC generator. So P equal to 4. Lap winding means parallel paths equal to poles, which is equal to 4. Useful flux per pole of 70 milliwebers. So flux is 0.07 webers or 70 milliwebers. Armature winding consists of 220 turns. So here you should be careful with this term turns. See, one turn will have two conductors. So you remember, so there is this one conductor and this another conductor. So one conductor is this and the other conductor together, it becomes one turn. So armature winding consists of 220 turns. That means Z is nothing but 220 turns multiplied by 2. So that will be 440 is the value of Z. And having resistance of 0.04 ohms. So each turn, so resistance per conductor, resistance per turn is 0.004 ohm. So therefore resistance per conductor will be half of that, so 0.002 ohms. But what exactly is the armature resistor, RA? So armature resistance is nothing but total resistance of the armature. Of course, that's what is the name suggests. But how is the armature constructed? So armature is constructed like this. So there will be how many parallel paths? There will be 4 parallel paths. And here how many conductors are there? So this is the 4 parallel paths. And then finally this will be the armature. So this is A and A representing the starting and ending terminals of the armature. 4 parallel paths are there. Now each path consists of how many conductors? So 440 conductors are there. So each path will have 110 conductors. So 110 conductors, 110 conductors and 110 conductors. And what is the resistance of each path? Each conductor, that is 0.02. So what is the total resistance? So let's first calculate this. So if I use my calculator, 110 multiplied by 0.02. So it will give me 2.2 ohms. So each one will be 2.2 ohms. So therefore by 4 I have to divide to get the RA. RA will be 2.2 by 4 because 4 parallel paths are there. So let me do that. Divide by 4. So I'll get 0.55 ohms. So this is the trick part in this question of determining what is the armature resistance. Alright. So calculate the terminal voltage. We're running at 900 rpm. So speed is 900 rpm with armature current of 50 amperes. So IA is 50 amperes. So first I want to find what is the EMF generated. So EMF generated is nothing but phi Z N P by A 60. So the flux that is given 0.07. Total conductors are 440 and the speed is 900 divided by number of poles. We have a 4-pole machine with 4 parallel paths. So this will give me EG. So zero point 0.07 multiplied by 440 multiplied by 900 divided by 60. So 462 is the induced EMF. So from this there will be a drop, IARA drop. So that will be here IA is given to be 50 amperes and the resistance is calculated as 0.05. So 50 multiplied by 0.55. So 50 multiplied by 0.55, that is 27.5. It feels rather large. So let's once again check. So 110 into 0.002. So it's actually 0.22, not 2.2. So this is 0.22. So therefore this will be 0.22 and therefore this will be 0.055. So I'm just following on correction. So how do I know where I made a mistake is that I got this 27 volts of drop, but typically armature drop will not be so high uh, uh, compared to this. So then I got a doubt whether I made a mistake. So that way you can actually do some self correction. So this will be 0.55. So obviously this will be 2.7 volts. And is there any brush drop given in this question? So it's not mentioned anywhere. So therefore I can find the terminal voltage. So will be EG minus IARA. So that will be 462 minus 2.7, that is 459.3, I guess. So this is the final terminal voltage of this thing. Calculate the terminal voltage when running at 900 RPM. So that is what was asked. So I think we had finished that part of the question. So I hope your answer is matching with my answer. So let's look at the next question. Here is the next example, that is example 10. So again, you can attempt this problem. So and check your answers with mine. You may pause it and try it yourself. So let me attempt it myself. So answer for this. Let's see what's given. A separately excited DC generator when running at 1000 RPM. So again, there's a 900 RPM also. So let me write N1 is 1000 and N2 is 900. Field, this is field, spelling mistake, supplies 180 amperes at 110 volts to a circuit of constant resistance. So load current is 180 amperes and load voltage 100 volts. What will be the current? Speed is dropped to 900 RPM and field current is reduced to 80%. So flux 2, so the moment field current is reduced, that means field itself is reduced. Field current and flux are proportional. So is nothing but 80% of flux 1. So or phi2 by phi1 is 0.8. So this is what is given here. Armature resistance RA is 0.04 ohms and brush drop is 2 volts. So we'll consider that. So first thing what I would like to do is find the EMF induced. So how to find the EMF induced? First IARA, so will be 0.04 multiplied by 180 amperes because this separately excited load current is exactly equal to the armature current. So let me calculate that. 0.04 multiplied by 180. 7.2. So 7.2 volts is the drop I am getting. Alright. Then brush drop is 2 volts. So therefore EMF generated will be the total output voltage plus the drop in the armature plus drop in the brushes. So 109.2 volts is the EMF generated. So let's denote it as EG1. So now we know that EG proportional to product of flux into speed. So therefore from this I can write Eg1 by Eg2 equal to phi1 by phi2 into N1 by N2. So in this everything is known except Eg2. So because phi2 by phi1 is 0.8, so phi1 by phi2 will be 1 by 0.8. Similarly, N1, N2. So N1 is 1000, N2 is 900. So I can write that. So this is 1000 and this is 900. And EG1 we just calculated 109.2. So EG2. So from this, I'd like to find what is EG2. So EG2 will be, okay, so first I'll calculate the right hand side. So I get 1000 divided by 0.8 divided by 900. So that quantity, I'm getting this one. This I have to make the inverse of it and then multiply it with 109.2. So I'm getting 78.624 volts. So this is expected. On one hand, the flux is reducing. On the other hand, the speed is also reducing. Therefore, EMF will definitely reduce. So that is 78.6 volts. So now under this new EMF, what will be the current if the speed is dropped to such and such value? So now, what is the load resistance I should know to calculate the current? So I think it helps if I draw this circuit. This is a separately excited. So this is VSH and this is ISH and this is the field resistance. Anyway, since this is constant, we don't have to worry about that now. So I have something like this now. So 2 volts will be the drop in the brush. I am generating 78.6 volts and the remaining the load resistance and armature resistance, which is 0.04. And then what is the load resistance? So from the previous results, I know what is the load resistance because IL is 180 and V is 100 volts. So V by 180 will give me the load resistance. So which is 100 volts divided by 180 amperes, 0.555 ohms. This is the load resistance. So now if I add these two, I'll get the total resistance in the circuit. So now based on this, I have to find. So effective voltage that is coming out of armature is 78.6 minus 2 volts. So I'll get 76.6 volts that is coming here. That divided by, so the current I will be 76.6 volts divided by total resistance 0.04 plus 0.555. So let's see how much it is. So to this I'll add 0.04 and then I'll take the inverse of it and then multiply it with 76.6. So I'm getting 128.6 amperes. So this is going to be the load current or armature current. So I think this concludes this problem. So I hope you understood how we are solving this kind of problem where separately excited DC generator is given. So kindly review this yourself. We'll do more problems. Let's look at example 11. So this is actually a problem taken from Electrical Technology Volume 2, example 26.20a. So in fact, other problems also are kind of derived from the same book, Electrical Technology Volume 2. So any standard electrical machines textbook will have many examples like this. So I strongly encourage you to, apart from seeing my videos, you can also get hold of a nice electrical machines book and look at the chapter on DC machines and DC generators and all. Like this, you will find several problems, so you can just for practice solve them. So speaking about practice, now we have this example 11 on your screen. So you can pause the video now, you can go to the question and you can try to solve this and you can check your answer with my answer. So meanwhile, let me begin my answer here. 4-pole DC shunt generator, shunt field resistance Uh, so DC shunt generator. So let me begin by drawing the shunt generator diagram. This is the armature resistance I'm just showing outside, and this should be a load. A 4-pole DC shunt generator, so P equal to 4. Field resistance 100 ohms, so this is 100 ohms. Armature resistance 1 ohm, so this is 1 ohm. Flux per pole is 0.2 Webers. If the load resistance is 10 ohms, so here the resistance is 10 ohms. Connected across the armature terminals, and the generator is driven at 1000 rpm, so speed is 1000 rpm. So the terminal voltage is not given in this. Calculate the power absorbed by the load. So the terminal voltage, maybe we'll have to calculate that. So let's do that. So first let's find the EG, EMF generated. So that is nothing but flux Pn. So here this information is also given, Z by 60 into A. So Z is, here it is given 378 wave connected conductors. So parallel paths will be 2. So whenever it is a wave connected, parallel paths is 2. Whereas lap connected, parallel paths will be equal to the number of poles. So anyway, so I have all these quantities now. So 0.02 multiplied by 1000 multiplied by 378 divided by 60 multiplied by 2. So this will give me the EMF generated. So let's do the calculation. So 0.02 multiplied by 1000 multiplied by 378 divided by 60. So again divided by 2. So I'm getting something like 63. So 63 seems to be quite less number. So let me once again check the calculation. 0.02 multiplied by 1000 multiplied by 378 divided by 60 divided by 2. So overall it is coming to 63 volts. Oh, I forgot to include P. So that is the problem. So again, you in this video you are seeing a lot of error checking. So the P is 4 poles. So here also I have to multiply by 4. See, because typically generators will have like 200 to 300 to 400, that kind of voltages. So suddenly 63 volts generator seems quite less. So that's the doubt I had. So 250 volts looks correct. So 252 volts is the EMF generated by this. So let me write it here, 252 volts. So brush drop is not mentioned, so there's no drop in the brushes. So therefore, because the voltage is not given, so we'll have to assume, so let the terminal voltage be V. So if the terminal voltage between, there's a 3 parallel paths now. So between any two, if I consider the voltage as V, so this is V. So then what is the current here? Current in the load will be V by R. Plus current in the shunt field winding will be V by 100. So will be equal to current in the armature winding. So how do I know the current in the armature winding? So total voltage, so 252 volts minus the terminal voltage divided by the armature resistance will give me the, see the voltage drop here is nothing but V minus 252 minus V, and divided by 1 will be the armature current, and the armature current will be equal to the voltage. So this is basically KCL. So the KCL is the entire thing. This particular term is the KVL. KCL and KVL together are used to get this particular relation. And this is one unknown and one equation, so I can find what is the value of V. So let's shift this V to the other side. So divide by 1 I can simply ignore. So I'll get V into 1 by 10 plus 1 by 100 plus 1. So this minus V go to the other side, become plus V is equal to 252. So let's, from this I can find V. So let's do that. So first I'll calculate 1 divided by 10. I get this plus bracket open 1 divided by 100 bracket close. So I get up to these two terms plus 1 again. So I get 1.11. This entire thing will go to the denominator. So I do 1 by x of this and then multiply it with 252. So I'm getting 227.02. So, or I'll just mention this implies voltage is 227 volts. So once I know the output voltage, what is asked in the question? Calculate the power absorbed by the load. So the load current will be V load by R load. So that is 227 by 10, 22.7 volts. So therefore load power will be V into I, that is 227 into 22.7. So that will be into 22.7. That will be 5153 watts. So this is the output power I'm getting. So this is similar to the other problem, but slightly there is a kind of a trick where without giving the terminal voltage, it is being asked. So if you come across any problem where terminal voltage is not given, so remember this example and you will be able to handle it properly. Now let's do example 12, and again you can try this problem yourself. So a 6 pole, it's not lab connected, it is lab connected. So this should be P. So a 6 pole lab connected, so I can right away write P equal to 6 and A equal to 6. DC machine has armature resistance of 0.18 ohms. So armature resistance is 0.18 ohms and generates 100 volts on no load at rated speed. So EG is 100 on no load at rated speed. Okay. Determine the armature resistance when the same machine is rewound using wave connection. What will be the no load voltage of the at the rated speed? So let's do this. So now there are 6 parallel paths. So let's say 1, 2, 3, 4, 5, 6. These 6 parallel paths are combinedly together giving a RA resistance of 0.18 ohms. So now when I do rewinding, I rewind with 2 parallel paths. So that means actually what I'm doing is the 6 parallel paths, I'm just connecting them in series. And then this will become one parallel path. And then this also connected in series. And then this will become another parallel path. So I connect these two, and this is my total armature now. So this is A and A, starting and ending of the armature. So this is what is happening when I convert a 6 pole lap winding to 6 pole wave winding. And obviously you see, so what is going to be the RA here? So this is 0.18 multiplied by 6, because if I want to find the resultant, I have to divide by 6. So here it will be 0.18 multiplied by 6. Again it is multiplied by 3. So each path will have that. So total will be, into 3. So each parallel path will have this resistance, and total 2 parallel paths are there. So now if I just divide this whole thing by 2, I'll get the RA. So RA with wave winding for the same conductors and same machine. So that will be 0.18 into 6 into 3 divided by 2. So each path, each branch will have, I'm just verifying the total resistance is this. So each branch will have that, and then into 3 will be this, and then divide by 2. Yeah, I think it looks correct. So this will go 3 times. So 0.18 into 9 is the answer. 0.18 into 9. So 1.62 ohms. Once again, 0.18 into 9. Sorry. Yeah. So 1.62 ohms is my new RA value. But then what happens with the EMF? You see, earlier the no load EMF used to be something like 100 volts is induced between these two. That means each branch you will get 100 volts. So here 100, here 100, and here 100. So total now voltage will increase by 3 times. So no load under wave winding will increase by 3 times. So this is your concept of converting a lap winding to wave winding. So I think no load voltage at rated speed and then wave connection. All right. So this is this example. So let's do one more example. So that is example 13. So again you can have a try at this and then see whether you can address this. So let me solve now. A DC generator has armature EMF of 100 volts. So EG equal to 100 volts. When flux per pole, I think for this problem, I'll denote this as EG1. Then flux 1 is 20 milliwebers. Speed is 900. So N1 is 900 RPM. So calculate the EMF generated when speed. So this is basically a very easy problem. So we know that EG1 by EG2 will be flux 1 N1 by flux 2 N2. So EMF is proportional to the product of flux and speed. So N2 is given to be 1000 RPM and same flux. So phi 2 is nothing but phi 1. So therefore, I can cancel these two and then find Eg2. So from this, Eg2 will be Eg1 into N2 by N1. 100 into 1000 by 900. So 111.11 volt. So this is the answer to the first question. Speed is 900 RPM. So now again the speed is going back to the same, whereas flux is 23 milliwebers. So N2 is again 900. Sorry, now I'll say N3 and phi 3 is 23 milliwebers. So therefore Eg3 will be Eg1 multiplied by phi 3 N3 by phi 1 N1. So from that I'll just calculate that. So Eg1 was 100 and flux is now 23 milliwebers and speed is same 900. So again 900 speed and the original flux it was 20 milliwebers. So this milliwebers will cancel, speed will cancel. So my answer will be 100 multiplied by 23 divided by 20. So it will be 115 volts. So this is just an application of this relation to solve this problem. So I hope you are again getting something from solving these problems. Let's do more. One more example problem. This is example 14 and let's try to do it ourselves. Okay, so what do we have here? A 4-pole generator, so P equal to 4 induced EMF of 250. So EG is already given. So 250 volts. When driven at the speed of 380 RPM. So speed is given 380 RPM. Armature is lap wound. So again, so lap winding. So A equal to P equal to 4. Has 652 conductors. So Z equal to 652. The armature resistance is 0.15 ohm. So the moment you see armature resistance, that means the problem is going into electrical parameters. So first, given all these things, I can immediately see that with this information, I can find what is the flux. So let's do that. So flux per pole is how much? So to find that, so I'll use Eg equal to flux into N into Z into P divided by 60 into A. So this relation. So from this, flux will be Eg into 60A by NZP. So 250 into 60 into 4 divided by 380 into 652 into 4. So this 4 will get cancelled. So let's calculate this. 250 multiplied by 60 divided by 380 divided by 652. So I'm getting 0.0605. 0.0605 Webers, or I can write it as 60.5 milliwebers per pole. So this is the flux per pole. Now, what is there in the question? The armature resistance is 0.15 ohm. The pole shoe has diameter of 50 centimeters. Each pole subtends an angle of 60 degrees at the center. So it is something going into the construction. So what is a pole shoe? So just imagine that this is a machine and this is a pole. This is the pole shoe. So what is the purpose of this pole shoe is first it will distribute the flux uniformly across a larger area, and another is if I have a winding here, it will protect the winding from moving. So it will provide some kind of a mechanical support here, so the winding cannot move down. So anyway, so what is given in the question is the pole shoe has diameter of 50 centimeters. So the diameter of this is 50. So this total diameter is 50 centimeters. So therefore from center the radius will be, so this is diameter, radius will be 25. So that's a different thing. Each pole subtend angle of 60 degrees. So if I take the center, this angle is 60 degrees. So from that I can find the this arc length of the pole. The length of the pole is 25 centimeters. So the depth, in other words, the depth it is given. So this is 25 centimeters or 0.25 meters. So determine the flux density in the air gap. So in order to determine the flux density, I need to know what is the total flux and total cross-section area. So how to find the cross-section area? So cross-section area will be arc length. So if the diameter is 0.5, what will be the perimeter? Perimeter will be pi d. But only 60 degrees I have to consider. So into 60 by 360, I have to take that. So only 1/6 it will be considered. So this will be the length of the pole. Or let's say width of the pole, WP. So pi d into 360, so pi diameter is 0.5, 60 by 360. So let's see what it is. So clear. So I have pi, this multiplied by 0.5 meters multiplied by 60 divided by 360. So I'm getting 0.26178. So 0.262 I take it as meters. So this is the width of the pole. Then length of the pole is 25. So 0.25 centimeters. So therefore area of cross section of the pole will be width of the pole into length of the pole. So that will be 0.25 into 0.262, or just to this I'll multiply 0.25. So I'm getting 0.065 meter square. So now I have the total flux. So flux density is nothing but flux per unit area. So flux is 60, so, or 0.0605 divided by, and this one is 0.065. So it might be slightly less than 1. So let's do that. I do the inverse of this, so 1 by x, and then multiply it with 0.0605. So I'm getting 0.924 Tesla. So this is the flux density of the pole. So this is a problem where it is slightly going into the construction of the machine. So but then finally we got the answer. So this is the answer. I hope you understood something from this problem. So similarly, I think in this entire 1 hour lecture, we had seen multiple problems. So each problem is trying to bring out some concept of EMF generation, and then based on the conductors, based on the poles, based on the lap winding or wave winding, how the EMF varies with speed. So all these relations we will try to highlight using this particular series of problems. So in this entire lecture 4, we had only looked at numerical examples. So let's continue this in the later videos. So I hope you are finding this useful. So if you find this useful, kindly subscribe to my channel, and you will find more videos in future. Thank you so much.